So in this video we're going to use the formulas that we came up with in the previous video to find a derivative implicitly. And in this case I want to find dy dx given that x squared plus y squared equals 9. So I need to implicitly differentiate this to find dy dx, and we should recognize this as a circle of radius 3. So I'm going to do this two ways. I'm going to do it the way that we've done it using Calc 1, and then we're going to do it using the formula right here to show that we get the same result either way. So a Calc 1 approach to this would be, hey, I have x squared plus y squared is equal to 9, and I want to differentiate this. I want to get dy dx, which means I need to take d dx of both sides. I need to take the derivative with respect to x of both sides. And if I take the derivative of 9, I just get 0. And d dx of x squared is just 2x plus d dx of y squared is going to be 2y times, by the chain rule or implicit differentiation, times y prime, because y implicitly defines a function of x, is what we would say. And then I need to solve it for y prime, which is the same as finding dy dx. We want to remember that y prime in this context means dy dx. So y prime equals, I'd subtract the 2x from both sides. I would divide both sides by the 2y that's on the y prime term, and then I would simplify and I would get the opposite of x over y is dy dx. And that was our Calc 1 approach, and the approach we've used up to this point for implicitly differentiating. But here's another way to look at it that allows us to implement this formula right here and the concepts that we developed in the previous slide. So if I have the relation x squared plus y squared equals 9, I could subtract 9 from both sides of this relation, and I would get x squared plus y squared minus 9 equals 0. And then what I can do is call this a function, right? X squared plus y squared minus 9 is a function of two variables, f of xy. So we let f of xy equal x squared plus y squared minus 9, and because x squared plus y squared minus 9 equals 0, this means that my function f of xy is equal to 0. And these were the two things that we needed when we developed this function. We needed a function f of xy that was equal to 0. So the moment I do this, if I want to know dy dx, what do I need to know? I need to know f of x, f sub x, and I need to know f sub y. I need to know the partial derivative with respect to x and the partial derivative with respect to y. And these are pretty straightforward to calculate. The partial derivative with respect to x of x squared plus y squared minus 9 is just 2x, because we treat the y squared and the 9 as constants. And the partial derivative with respect to y of x squared plus y squared minus 9 is just going to be equal to 2y. Because x squared is a constant when differentiating with respect to y, we hold the x as constant, and minus 9 is clearly a constant. And so from here we know that dy dx is just equal to the opposite of f sub the derivative with respect to x in the numerator divided by the derivative with respect to y in the denominator, and that simplifies to negative x over y. We get the same result that we got using our Calc 1 techniques. We took a different approach to it. In the next video we're going to look at a function of 3 variables, which I think is, for our purposes, the more useful context, and we'll see where this gives us some advantages.